Welcome back to I Can Science That. We are sciencing the Rayleigh Criterion. The Rayleigh Criterion gives us an angular size that an object appears visually so small that we can no longer resolve it. That leads us to the obvious next question and the subject of today's video. What does it mean to resolve something? We all know that when an object goes farther into the distance, it becomes visually smaller. Leads to what we often describe as a vanishing point. So that leads us to the question, if there is this vanishing point, where is that? How far away does an object need to get before we just cannot see it anymore? It's a natural question to ask, but it actually belies a misunderstanding of how vision actually works. Let's take a closer look at what it means for something to be too small to resolve, and we'll see that that actually does not mean it becomes invisible. So let's start with a pixel resolution analysis. I just grabbed a picture of the sun taken with a solar filter. What if this object were farther away and we took the same picture with the same camera? The object would be smaller. I think we're all aware that a digital camera, the sensor, is an array of pixels, little squares that are detecting the light. In this high-resolution image, those little squares are so small that we don't really see them. But if we zoom in on something that's much smaller, it'll have fewer pixels to it. If we zoom in far enough, we can see the individual pixels. Let me give you an example like this. What I've done is simulate the effect by using a lower resolution version of this image. If we zoom in this far, each of the individual pixels is clearly visible now. We can still see that it looks round, but not as round. Let's keep going. What if the object were even smaller on the sensor and we had to blow up even further? Here we have just a jumble of pixels. It's a jumble of pixels and you can no longer tell that it is round. The individual pixels are too large to carry the information of exactly what the shape looks like. We know that there's light from a light source hitting this pixel, but what is the shape of the object that is causing that light is very hard to tell. What if we keep going? Let's take an image of an even smaller distant object and see when it approaches that vanishing point. Here we have an image of a distant light source that is only affecting a single pixel. This is a single pixel now of the image, and we can still see the light from that light source hitting that pixel. We just cannot resolve what that object is. There is now no further information at all other than that there's light, the intensity of the light, the color of the light. We get that, but the shape of the object is completely unresolvable. That's what it means when an object cannot be resolved. It does not mean the object is invisible. The light doesn't just stop coming to us. It's just that with the resolution of our sensing equipment, we can't make out the shape of the object. For giggles, let's keep going. Let's go out even further and see what happens if we keep blowing out even further. We'll see that this giant pixel here has detected some light. So even then, we still are seeing that there is a light source somewhere in the upper left corner of that image. We just cannot resolve any further detail than that. There's a light source there, and that's all we know. There's no specific cutoff line where you can no longer see the light from a distant object. The light from the distant object will still come towards you, and if it hits one of your sensors, you can detect it. You just can't see the shape of it anymore. So once the object, the full angular size of your distant object, is smaller than 1 pixel, then it is completely unresolvable. It's just going to come in as a pixel. And if it's not at least a handful of pixels, you won't be able to make out anything about the shape. So that's what happens with my simulation of imagining that this star were actually farther away and we were taking a picture and zooming in. Let's instead take this actual image now and zoom in on it and see how small an object we can resolve using this image. Here's the original size, and if we zoom in a little bit, we can see right here, there's a little dot, a little speck, like a sunspot or something. Let's zoom in on that object. There's definitely multiple pixels of resolution there. Let's keep going. And if we zoom in to where we're looking at individual pixels, we can now make out the shape of that object, and we can resolve that object. But I think you can agree that if we wanted to zoom in any further and try to break in further details about what the shape of that object is, we would not be able to with this image. The pixel resolution of this image is not enough. There's not enough information to see what exactly the shape of this pixel here is. We know that there's something there, but we don't know what its shape is in any more detail than this. So that is what it means to resolve something in terms of pixels. But the human eye is not based on like pixels. We don't have CCDs in our eyes. We have a retina. There are cells, photoreceptors, aligning the back of our eyes, and that's what we use. So let's take a look at how that works. I think most of us have seen something like this in our time. I certainly have. This is your classic eye chart where the eye doctor will ask you to read a line, and over here we see the vision numbers that are quoted, like 20/20. What is 20/20 vision? That's what we're looking for. You have 20/20 vision. That means you can read that line. Let's zoom in a little bit on this area. We'll zoom in and so that you can get a better sense of what we're talking about. So this is what it might look like if you have 20/20 vision. If you have good vision, you can resolve that this is the letter D, this is the letter E. It's fuzzy, right? It's not perfect. It's a little bit fuzzy, but it's clear enough that you can resolve the differences between the lines and the white patches and make out enough detail to read those letters. If you can read those letters at the distance that the eye doctor puts you, then you've got 20/20 vision. Let's zoom out a little bit. We'll push you back. You walk backwards and take another look. This is maybe what you'd see. Something that looks like this. It's much blurrier. At this point, we're starting to wonder, is that a D or a P? And you're starting to second guess your answers. It's getting difficult to resolve enough detail that you can confidently say what those letters are. If we step further back, it becomes even blurrier, and you can now maybe barely make out that there are letters here, but you certainly cannot read what they say. On the other hand, let's point out that this bold red line is still very distinct, very bold, and obvious that it's still there. So the letters themselves have not completely vanished. We see that there are like dark smudges in this area that may lead us to believe perhaps there's text there, but we certainly can't read it. That's what it means when something is beyond the limit of being able to resolve something. And the eye doctors tell us that what they're looking for in this 20/20 vision is a visual resolution of 5 × 10⁻⁴ radians. What does that even mean? In terms of degrees, we have this size, and here it is, 1.72 arc minutes. 3 different ways to measure the angle between two things. And what we're talking about is like the angle between the top and the bottom of the D, or maybe the angle between this little notch in the E. When that little notch in the E becomes less than 1.72 arc minutes in size, then even a 20/20 vision person would not really be able to see for sure whether they were looking at a notch in an E, or was that maybe just part of the straight line of the E. Those are the sizes that are no longer resolvable. So that 20/20 vision, how does that compare with what we learned about the Rayleigh criterion? The Rayleigh criterion for an eye, it varies. We saw before that it varies based on the wavelength and the brightness of the room, but a typical value that might be quoted is about 1.2 times 10 to the minus fourth. And what does that mean in degrees? It's this number, or it's 0.4 arc minutes. What we had just said was that the human eye for 20/20 vision has a resolution of 1.7 arc minutes, but the diffraction limit predicts 0.4 arc minutes, which is much smaller. In other words, the diffraction limit of the eye is good down to an even smaller size than most people can see. Most people can see about 0.03 degrees, but the diffraction limit is 0.007. So you should be able to see something even smaller if your eye was limited by the Rayleigh criterion. So clearly your eye is not limited by the Rayleigh criterion. Instead, the typical human eye is limited by the density of the photoreceptors in your retina. Like with a digital camera, it is the resolution of your sensor that is limiting your vision. We have seen that when something gets in the distance, it becomes smaller visually. It will take up less pixels in your sensor, and that means you're going to struggle to make out details, but the object will not actually vanish. The object will still appear to be there as perhaps just a blurry shape. Whether or not you can still see it is going to be dependent on how much contrast there actually is between that color, that blurry color that you see, and the colors around it. We have also seen that the typical human eye is not limited by the Rayleigh criterion, but is instead limited by the density of the photoreceptors in the back of your retina. This also gives us a guideline for good camera design. If you're going to design a camera for use in telephoto situations, you can increase the resolution of the sensor at the back of the camera up to a point. At a certain point, increasing the resolution of the sensor will not help you because the size of the aperture will become the limiting factor through the Rayleigh criterion. And so then by the same token, increasing the size of the aperture will open up that Rayleigh criterion, allow you to resolve smaller objects, but then you need a higher resolution sensor in order to take advantage of that. And that is, in fact, how high-end telescopes are created. We need a much larger aperture to see much smaller objects. And to go with that, of course, we need insanely high resolution sensors. All right, that's it for video number 2. I'll see you again in number 3.